Hello and welcome to the next video in our series. Thank you so much for joining me. This is the Essential Skills for Physical Science series, focusing on paper 1, the physics paper, to help you prepare for your final matric exams. I'm Dr. Derek Fish. I've been director of the Science Centre at the University of Zululand for the past 30 years. This is video 6.5, again looking specifically at equations and the skill of solving equations, but focusing on equations for work, energy, and power. And you'll find this from pages 52 to 54 in your booklets. Just before you turn to page 52, as always, we're going to start on page 3, your contents page. So if you can turn there and just see where this section is located. Remember, we're looking at essential skills. We've looked at graphs, free body diagrams, equations. We will look at multiple choice. And within the equation section, we're zooming in on the equations on work, energy, and power. Now, this is always question 5 in your final exam, and it's just 3 pages from pages 52 to 54. Why are we spending so much time on equations? Well, as we pointed out in the introduction, they form more than 60% of the marks in paper 1. And in the examiner's report, there's this note that learners still cannot work with scientific equations and formulae. And the only way for us to do this is to practice. On page 4 in your booklets, remember in the bottom right-hand corner of the screen, you'll see the page number, which is in the top right-hand corner of your booklet. Where do we find work, energy, and power in the curriculum? Well, it's in the mechanics section. You started it in grade 10, where you were introduced to energy, gravitational potential energy, kinetic energy, mechanical, and the idea of conservation of mechanical energy. Then you were looking at in the absence of dissipative forces like friction. And then in grade 12, you return to work, energy, and power, looking at the work energy theorem, and also looking at what happens with non-conservative forces like friction present. Don't forget the grade 10 work, which was an important introduction. So looking at the last 3 papers, which we've averaged, as I said, question 5 is always on work, energy, and power, part of the mechanics section. And on average, over the last 3 papers, it's counted for 14 marks. This is a snapshot of question 5 for the last 3 papers, and you can see something in common. It's always dealing with an object on a slope. So obviously, we'll be looking at conservation of mechanical energy, and we're looking at potential energy high up the slope, kinetic energy at the bottom. You can see that usually there's some friction on the slope, so there are non-conservative forces present. We will take a detailed look at all these 3 questions. And then just finally on page 5, what sort of skills do you need? Well, this is the CAPS summary of skills for physical science. And for question 5, you'll obviously need to understand your scientific notation and your metric prefixes. You'll be looking at maybe megawatts, kilowatts, and so on. We'll have to change the subject of a formula. That's a skill you always need for equations. And you will need some basic trigonometry skills. You'll see, particularly when we define work, it's defined in terms of cos theta, the cosine of the angle between the force and the movement. And then, of course, we need to understand rate, because power is an example of rate. It's the rate of doing work. So once again, this is the Essential Skills series. This video is not intended to teach you work, energy, and power. You should have done that already. Use your notes, use your teacher, use your textbook. But we're going to focus on the skills. Why? There's again a comment from the examiner in the exam report. A severe lack of skills is evident. Mathematical, conceptual understanding, and integration of topics. Free body diagrams, graphs, and equations. We're going to focus now on the skill of equations for question 5 on work, energy, and power. So before we get into the details of the equations, let's try to understand energy conceptually with just a brief revision of some of the main concepts. And again, please make sure that you have been through this section carefully from your teacher, your textbook, and your notes. This is just a very basic revision. Energy is probably the most important concept in physics, and without energy, nothing would happen. There's many different types of energy like mechanical, thermal, electromagnetic, electrical, chemical, and nuclear, and these are all examples of those. But you know, physicists quite often like to classify energy into just two types: kinetic energy, involved with movement, and potential energy, involved with stored energy. So in all these cases, there's something moving. Photons of light energy, the gear wheels in a mechanical system, air particles in a sound wave, electrons flowing through a wire with an electric current. We know with thermal energy that the average kinetic energy of the particles increases. And with potential energy, there is stored energy. Now, all the machines we have which make the world work simply convert energy from one form to another. So when you ride a bicycle, you're converting the chemical energy from your food into mechanical energy. A torch converts chemical energy from the battery through electrical energy into light energy. In a car, chemical energy in the petrol is converted into mechanical energy. A light converts electrical energy into light energy. When the sun shines on plants and causes photosynthesis, we see light and heat energy converted into chemical energy and growth. And finally, a toaster converts electrical energy into heat energy. Let's investigate these energy conversions a little bit more with this fantastic simulation from PHET called Energy Forms and Changes. Again, teachers, this is in your teacher pack. So as well as watching the video, please investigate this by yourselves because you'll learn much more that way. In the simulation, you have something or someone creating the energy. You have a generator which converts energy from one form to another, and you have something using the energy. So if I start the cyclist pedaling, you'll see that pedaling turns the generator, which creates electrical energy, which lights the element here, and you can see the temperature is rising here. Now, of course, you don't get energy for free. And after a while, the cyclist becomes tired and cannot actually create any more energy. Then you need to feed the cyclist, and that chemical energy will allow the cyclist to do some more work. Now, it's very easy to change these. We can change the cyclist for a tap, and we can allow the energy of the falling water to turn the generator. Or we can change it for a kettle, and as we heat the kettle, the steam that's created, that thermal energy, will also turn the generator. Similarly, we might want to try a different sort of generator. If we have light energy from the sun, that's not going to turn this generator physically, but if it shines on a solar panel, it can create electrical energy. And then we can use this to heat water, to light a conventional light bulb, to light a low energy light bulb, or to turn a fan. So play around with this. What's quite useful is you can put on the energy symbols here. Let me just hide myself so you can see them better. And they identify 5 types of energy: mechanical, electrical, thermal, light, and chemical. So going back to our very first example of the cyclist actually heating the water, if we start it up, you can see that the green chemical energy gets converted into the gray mechanical energy to turn the generator. That becomes the blue electrical energy, which passes into the element here and heats it up, where it becomes the red thermal energy. So you can follow the energy changes here. As we put some food in, chemical energy becomes mechanical energy, becomes electrical energy, and becomes thermal energy. Now, I think it would be quite a good exercise for you to try to identify different energy types and energy changes. So I'd like you to pause or stop the video here for 5 minutes while you try to identify the energy changes in these 4 examples. So these are 4 screenshots from PHET. So a kettle is heated and the steam makes electricity to light a light bulb. The second one, solar energy turns a fan. And the third one, falling water generates electricity to light a bulb. And the fourth one was the one we started with, the cyclist turning a generator to heat water. Now here are the 5 types of forms of energy. And you can just use the first letter, M for mechanical, E electrical, T thermal, L light, and C chemical. So for each one, I'd like you to try to write down, just with the letters, the energy changes that take place as you move from left to right. So please pause the video here for 5 minutes. Let everyone try that in groups, and then we'll go through the answers. So for number 1, we have the kettle being heated, the steam turning the wheel, producing electrical energy to light a bulb. So we can say thermal energy, heat energy, becomes mechanical energy as the generator turns, which becomes electrical energy in the wire, which becomes light and thermal energy. Maybe you left out the T, but don't forget, you all know that if you touch a light bulb, you'll burn your hand, because it's not just light energy that's created, it's also thermal energy. Before we do the others, let's look at this in the actual simulation. So I switch on the heat source. That causes the kettle to boil. The rising steam turns the wheel of the generator, which creates electrical energy in the wire, which lights the light bulb. To make it easier to see these changes, let's turn on the energy symbols. Here you can see the thermal energy becoming mechanical energy, and then the blue electrical energy in the wire, and that heats up the filament of the bulb, thermal energy, and escapes as thermal and light energy. So that's the first example. Let's go straight to the second one, and I want to do it in front of you and show you just how easy it is to set up this PHET simulation. So in the second case, we're going to have some sunlight. Now, of course, sunlight will be no good for mechanical generator, so we need a solar panel, and in this case, we're going to get it to turn a fan. Switching on the energy symbols again, you can see we have light energy from the sun, and through the photoelectric effect, part of your matrics syllabus, it becomes electrical energy in the wire, and that becomes mechanical energy as the fan turns. Let's go straight to the third example. Here we need a source of water. Now, of course, water falling on a solar panel is not going to do anything except damage it. So we need a mechanical generator, and we're going to put in a low energy light bulb here. Now, again, the energy symbols are there, and you can see mechanical energy from falling water gets changed by the generator into electrical energy in the wire, which becomes mostly light energy with a low wattage bulb, but also some thermal energy here. And straight on to the last example, which was in fact the one that we started with. If we allow our cyclists to pedal, you can see the chemical energy, stored energy from food in the body becomes mechanical energy here. That's converted by the generator to electrical energy. And as it heats up the element here, that becomes thermal energy in the water. When the cyclist gets tired and we feed the cyclist, we create some more chemical energy, and the whole process can start again. So just to recap the other examples in case you didn't get it, if you look at number 2, we have a change from light energy to electrical energy to mechanical energy. Number 3, mechanical energy from the falling water to electrical energy in the wire to light and thermal energy coming out of the bulb. And number 4, chemical energy in the body and from food becomes mechanical energy, which becomes electrical energy, and then thermal energy in the water. So that's a great way to explore energy conversions. Now we also want to have a look at the basics of mechanical energy, kinetic and potential energy, and we'll do this with another great simulation, which is called Energy Skate Park. You can either use the basic or the advanced form. So here's the energy skate park, and we can change various things and show various displays, but we've got a skateboarder who can slide down a slope here, changing potential energy into kinetic energy. Now we can put up a pie chart on the skateboarder, and you can see how that potential energy changes to kinetic. It's possibly easier to see with a bar graph, and let's make our skateboard a little bit heavier. So if we start at the top here, start out with potential energy, which becomes kinetic energy. Fortunately, we can do things in slow motion. So let's do that again. Potential energy gets less as the skateboarder gets lower, and that becomes kinetic energy. You'll see that the total energy, which is the total mechanical energy, stays the same here. We can also put up a speed meter, and again, you'll see that obviously the speed is 0 at the top, and the speed increases towards the bottom here. So this is a great way to investigate. And so once again, if we take our skateboard and put him at the top, the energy is all potential, and you'll see the potential energy decreases because it gets converted into kinetic energy, but no energy is actually lost here. If we choose a different track, you can see that if we put our skateboard at the top, again, it's all potential energy. And watch how that is converted into kinetic energy at the bottom, back to potential energy. So this is similar to a pendulum. Potential, again, back to kinetic and back to the top. Now, if I stop the skateboard about halfway down, you'll see that there's a mixture of kinetic and potential energy. But those two added together would give us the same total energy. So at the top, it's all potential. At the bottom there, it's all kinetic. And at the top, you'll see it's all potential energy. In between, we have a mixture of potential and kinetic energy. And even if we make the track more complicated, it doesn't really matter. But you'll see there's this change going on all the time, changing from potential energy to maximum kinetic. And then in between, you get a mixture of potential and kinetic energy. So the problem with this is looking at an ideal world where we only have conservative forces like gravity, but in the real world, it never works like this. So let's choose to add some friction here. We'll start off with no friction and just remind ourselves that if we have a look at our bar graphs, if we put our skateboard at the top of the ramp and release him, all that potential energy gets changed to kinetic energy. But what happens if there's some friction on the track? Let's have a look at that again. We start our skateboarder off. Right, let's reset our skater. And you can see as he goes down, we get some thermal energy. And in fact, the kinetic energy gets less and less. Now he's gone off the picture. So let's rather choose this track here. Again, starting off with no friction. And we'll let our skateboarder slide up and down the track. Now what we've seen is this perfect conversion of energy. But let me put some friction on the track. And what we'll start seeing is an increase in thermal energy here. In other words, the wheels on the track and the skateboard are getting hot. Now what you'll start noticing is he doesn't go all the way back up to the top. And his speed at the bottom is not what it once was. And eventually, all that useful energy gets converted into thermal energy. And that thermal energy, of course, is just radiated into the atmosphere and is no use. So this is the reality. Let's have a look at that one more time. You can see he started with maximum potential energy, but already he's lost some. And if we put the speed on, we'll see the speed at the bottom is not as much as it was before, and it gets less every time. So what we see is that we don't conserve mechanical energy. Some of it is lost to this thermal energy because we have non-conservative forces taking part. Let's take a look at the equations for this section on work, energy, and power. Now you'll find these on page 52 in your booklet. But before we go there, perhaps turn back to page 37. And there I proposed the progress method for problem solving. And this method will help you with equations in all sections, from questions 2 to question 10 in your exam. Just to recap again, it's quite often helpful to draw a picture, especially for these energy questions, especially for objects on a slope. Quite often there's a good picture in the exam paper, so you don't need to redraw it, just add to it. And always check carefully what is required. What are they asking you for? I've highlighted that in green. Then look out for the obvious, for example, the acceleration of gravity. They would expect you to know that and might not state it in the question. Then check carefully what is given, what information are you given, and look out for things like from rest, which means velocity equals naught. Then you need to relate what is given to what is required by choosing the correct equation, and then you substitute and solve carefully. Now, how do we find our correct equation? Well, on page 38, we have our data sheets, and halfway down on page 38, we have the equations for work, energy, and power. And these will always be associated with question 5. Now, I find the layout here on page 38 for these equations quite confusing. It looks like there are far more equations than there really are, because you can call kinetic energy K or EK. You can call potential energy U or EP. They've got English and Afrikaans. And in fact, if I do that, these are the only equations which are important. And if we just put them all together, you'll get a much smaller box like this. I would suggest you use U for potential energy and K for kinetic energy. It's much simpler than using subscripts. And then it reduces to these few equations: kinetic and potential energy, the equation for work, the work energy theorem that net work done is a change in kinetic energy, the work done by a non-conservative force, and then 2 equations for power. So it's much simpler this way. Let's look at them one by one. Before we get to equations, we need to consider the variables. Now, there are actually 11 variables which are commonly used in these equations, and 1 constant. So the constant at the bottom, the acceleration due to gravity, 9.8 meters per second squared. Now, many of these variables are very familiar to us by now: force, mass, velocity, height, displacement. Angle theta is between the force and the displacement. That will become clearer when we see the diagram. And time. So here are the quantities especially associated with this section: work in joules, and with the subscript net, it's net work, and NC, it's work done by a non-conservative force. Then we have power in watts, and a watt is just a joule per second. Kinetic energy and potential energy, because they are energies, they are just measured in joules as well. And EM is mechanical energy, which is a sum of kinetic and potential energy. Now, it's important to consider which of these are vector and which of these are scalar quantities. Remember, a vector needs magnitude and direction, a scalar magnitude only. And you might be surprised to find the ones I've highlighted in red are all scalars. And in fact, all these work, energy, and power quantities are scalars. So you do not give a direction for kinetic energy or potential energy or work or power. The only vectors we deal with are the force, the displacement, and the velocity. So starting off with work, the problem with defining work is you probably think you're doing work right now, sitting watching the video, but in terms of physics, you're not. So let's look at some examples. So a girl pushes a box along the floor against the force of friction. Is she doing work on the box? Yes, because there is movement in the direction of the force. Take an example: a girl walks with a backpack at a constant velocity. She obviously has to provide an upward force to hold the backpack up. Is she doing work on the backpack? No, because the direction of motion is at 90 degrees to the direction of force. Thirdly, a girl picks up a bag of groceries. Is she doing work? Yes, because the direction of the force and the direction of the motion are the same. And fourthly, similar to the second one, a girl walks forward holding a bag of groceries. She's not doing work on the bag of groceries because the direction of motion is at 90 degrees to the direction of the force she applies on the bag. So we have this definition: work is done when a force acts on an object and causes it to move in a direction parallel to the force. And that movement is very important. By just holding something up, you're not doing work on it. So we draw a diagram like this, and if the force is not exactly parallel to the displacement, that's fine. We write it as work equals F delta X cos theta, where theta is the angle between the direction of the force and the direction of the displacement. Now, power is simply the rate of doing work, so it's just work over time. How many joules of work are you doing per second? Power is often measured in kilowatts, but normally just in watts. And then in the case where a force moves an object at a constant velocity, we can calculate the average power needed to do that is equal to force times average velocity. Again, all these equations will become clearer when we do actual exam examples, but these are all there on page 52. So just to think about work a bit more, the pylon that's holding up these electrical wires is not doing work on the wires because it's not moving them. But a wind that causes the cables to move is doing work. The brackets that are holding a shelf up, although they're providing a force to hold it up, the shelf is not moving, so no work is being done. But if you push a trolley against the force of friction, you are doing work because you're moving in the direction of your force. Similarly, the tractor is moving in the direction that the log is being pulled, so it is doing work. An interesting example, if you swing a stone around on a string, the tension in the string pulls it inwards towards your hand and constrains it to go in a circle, but that tension is not doing work on the stone because the movement is a tangent to the circle and is always at 90 degrees to the tension force. In the same way, the force of gravity that the Earth exerts on the moon does not do work on the moon because the movement of the moon is at 90 degrees to that force. Then let's talk about mechanical energy. So we looked at this energy skate park from PHET before, and we learned about potential energy. Now, if an object of mass m is at a height h above the ground, potential energy you can call EP or U. I suggest you use U, is just the mass times g times h, the height. Kinetic energy, when it's traveling at a velocity v, is just half the mass times v squared. So velocity is very important in calculating kinetic energy because we're squaring it. A small increase in velocity leads to a large increase in kinetic energy. If you double your speed in a car, your kinetic energy becomes 4 times as much. That's a good reason to obey the speed limit. And then, of course, we have mechanical energy, which is the sum of potential and kinetic energy. So in this case, with no friction, your total energy here is just your mechanical energy, and it's a sum of potential and kinetic. So EM equals U plus K, and it's constant as long as there's no friction or dissipative forces causing energy to be lost. If we're dealing with a force accelerating or slowing down an object on the ground, so in the case in which work is done and the only change in the system is in its speed, not its height, then the work done, the net work, is equal to the change in the kinetic energy. Net work done equals delta K. So it's the final kinetic energy minus the initial kinetic energy. We call that the work energy theorem. Now, something that can be confusing is to consider conservative and non-conservative forces. Perhaps the best way to think about them is in terms of examples. Conservative forces, the most common one you'll come across is the gravitational force, also electrostatic forces. Non-conservative forces are typically friction and the applied force, the tension force. With a conservative force, the work done on an object does not depend on the path taken, and the energy is recoverable. So whether you get into a building by walking up steep stairs or going up a sloping wheelchair ramp, the same amount of work is done against gravity because it's a conservative force. But obviously, if there's a frictional force, it makes a big difference if you take a longer path because then more friction will act and more work will have to be done. And in this case, the work done does depend on the path taken, and the energy is not all recoverable. So we often call these non-conservative forces dissipative forces because they permanently take away energy from the object. And it's not lost, but it's changed into forms which are not useful to us. Now, again, if you look at mechanical energy, where you have conservative forces, mechanical energy is conserved. So in the absence of friction, mechanical energy is constant, and that's just the sum of potential and kinetic. So the change in mechanical energy is 0. Where you have non-conservative forces, we can calculate that the work done by a non-conservative force is equal to the change in the total mechanical energy. So that's an important equation for you. Work done by a non-conservative force is the change in kinetic energy plus the change in potential energy. You'll see there is a calculation like that in every exam question. So we discussed this, the idea that when you include friction into the mix, mechanical energy is not simply conserved, and some of it is changed into thermal energy, which is not useful. So in the absence of friction, mechanical energy is conserved, but where there's a non-conservative force, the work done by that force, usually friction, is equal to the change in the total mechanical energy. So just to make that point one more time, if we switch off friction, as I've done here, which is of course not realistic, you can see that total mechanical energy is conserved. And this total energy is either all potential at the top, or when it gets to the bottom, it's all kinetic energy with a maximum speed, or about halfway up, you can see it's a combination of kinetic and potential energy. If I switch friction on, we'll see that something different happens here. And as the skater skates down here, because of friction between the skateboard and the track, some of that energy is converted into thermal energy, and that thermal energy cannot be recovered. So you can see it's a dissipative force, the force of friction, and you can see the speed is less, the height is less, kinetic and potential energy are less, and gradually all of that initial total energy will be converted to useless thermal energy. Just a note about friction in closing. You can see here a chemistry book and a physics book. There's always a bit of friction between physics and chemistry. And at an atomic level, you can see that there are particles on the surfaces. And if we move that chemistry book from side to side, there's potential for these particles to rub against each other. Now, at the moment, I'm not pressing the books together. But if I push down on the chemistry book and then rub together, you can see that it leads to increased motion of the particles and an increase in temperature. And that's what friction does. It takes useful energy and converts it into wasteful heat energy. Now, you might be quite overwhelmed by now by all these equations and variables. You need to get lots of practice in using them, but let's get some practice now by looking at some previous exam examples. Let's start off with an illustrative exam example, which I will do for you. And then there are 3 from recent final exams, which you can try, and then I will help you with. So this one comes from the KZN preparatory exam, September 2020. It's not in your booklet, so just pay attention on the screen. Normally this question is for about 14 marks. This one was for 19 marks. So it was quite a big question. It actually had 2 parts. One, a truck on a slope, looking at non-conservative forces, and another one, 2 cars about to collide, looking at the work energy theorem. So here's the question, and as I said, it's not in your booklet, so just pay attention on the screen. For the first part, a truck of mass 1,200 kilograms is moving down a rough inclined track. It has a speed of 0.8 meters per second at point P, which is 1.8 meters above the ground. From Q to P is 2.2 meters, and when the truck reaches point Q, it has a speed of 4 meters per second. Now notice the word rough. That means there's friction. So 512, is mechanical energy conserved? Yes or no? No, because we have friction. We have non-conservative forces present. 513, use energy principles. Now this can be done with equations of motion, but please don't, because you will lose marks. The examiner stresses that you must use energy principles. Let's focus on what is required to calculate the frictional force acting on the truck as it moves from P to Q. Let's zoom in on 5.1.3. Now, the first thing in our progress method is a picture. There is a picture here, but it can be very helpful just to add a couple of things. Speed at P is 0.8, speed at Q is 4. We've got the height at P. The height at Q is obviously 0. And I've highlighted in red all the given information. So we've drawn our picture. We've worked out what is required, calculate the frictional force. What is obvious, for example, that the height at Q is 0. And all the given things are highlighted in red. So now we need to look for an equation to link what is required with what is given. And the frictional force is a non-conservative force. So the work done by non-conservative force, which is just the work done by friction on the truck, is the change in kinetic energy plus the change in potential energy. So that's just the kinetic energy at Q, the end point, minus the kinetic energy at P, the beginning point, plus the potential energy at Q, which we know will be 0, minus the potential energy at P. Again, I've highlighted all the variables in red, which are given, and those in blue are the obvious ones like G, the acceleration of gravity, and HQ, which is 0. Sometimes the hardest thing in these questions is just to keep track of all your numbers. So filling in the numbers, 1200 comes up time and again, that's just the mass. And then it's useful to have the velocities on the diagram, because you can see that the final velocity is 4. Initial velocity was 0.8, so you can calculate the two kinetic energies. And then when you look at potential energy, the final potential energy will just be 0. And the initial one was mass times g times h. When you work it out, it's not difficult, but just has to be careful. You'll get that the work done against friction was work done by friction on the truck was minus 11,952 joules. It's negative because the truck is moving to the left, but the force of friction acts to the right. But be careful, the question said calculate the frictional force, not the work. We must remember that work done is force times cos of theta times the distance. We know the distance traveled is 2.2 meters. So the force of friction is what we're actually after. And when we put in 11,952 that we get from the previous answer, we put in the distance, we get that the force of friction is 5,432.73 newtons. So calculate the frictional force acting on the truck as it moves from P to Q. This might look very confusing. Just go through it slowly. You can just rewind and replay the video, pause it when you need to. Just make sure you understand where each of these numbers comes from. Second part of the question was completely different. You've got a 1,000-kilogram car traveling along a highway at 35 meters per second. That's somewhere around 120 kilometers per hour. He applies his brakes to avoid hitting a van in front of him, which is completely stationary. After the brakes are applied, a constant frictional force of 8,000 newtons acts on the car. So that's the braking force. Now, there are two parts to this question. In the first part, 522, they want you to calculate the minimum distance required for this car to come to a complete stop without hitting the van. In the second part, they assume that the distance is not enough, the distance of 30 meters, and they say the car is going to hit the van. At what speed will it hit the van? Now, in both cases, we're going to use the work energy theorem like that. The net work done is equal to the change in kinetic energy. There's no potential energy involved because it's all on a flat road. So in the first part, the final velocity must be 0 because the car on the left must come to rest. We don't know what the minimum distance required is. We want to calculate that. So please notice that's what is obvious and that's what is required. Now, in this case, just to be complete, for the net force, we've put the work done by friction on the car. We've also put the work done by gravity and by the normal force, although those are both going to be simply 0 because there's no movement in the vertical direction. So gravity and normal will be 0. And the change in kinetic energy, the final velocity is just 0, so that term is going to be 0, and we subtract the initial kinetic energy based on 35. So again, make sure you're aware where all these numbers come from. 8,000 newtons was the force of kinetic friction. You were given that. Delta X we're looking for. 1,000 is the mass of the car. Final velocity is 0. Initial velocity is 35. So we do the calculation and you'll get that delta x is 76.56 meters. And you can see where the 4 marks are applied there. So notice this, that actually the distance, the minimum distance required, depends on the square of the initial velocity. Again, this is good reason not to drive fast. If you double your speed, you actually require 4 times the minimum distance to stop. Now, for the second part of the question, notice what has changed. In this case, the distance is given 30 meters. In 522, you're asked to calculate the distance. In this case, the final velocity is unknown. We assume that the car on the left will hit the truck. We don't think that he'll stop in time, so we want to know at what final velocity does he collide with the truck. Otherwise, we do it in the same way. Work energy theorem, net work done is equal to delta K, the change in kinetic energy. For completeness, we include work done by gravity and normal force, although they will both be 0. And in this case, the final velocity is what we want to calculate here. We don't know that. So work done against friction is a frictional force 8,000 newtons, cos 180, because the two forces are the forces in the different direction from the movement. Look at those two arrows. So it's 180 degrees. And 30 is delta x. That is all the distance which is available. Then 1,000 is the mass of the car. Final velocity we want to calculate, and 35 is the initial velocity. You can see that a good drawing with arrows and labels on it is very helpful. Do the calculation, and we can calculate that the final velocity would be 27.29 meters per second. Now, that's equivalent to about 100 kilometers per hour. So you can see that a 30-meter stopping distance is just simply not enough if you're traveling at about 120. So that's a fairly straightforward question from the KZN Preparatory Exam 2020. Now we'll move on to some questions which you can try. So now it's time for you to try some exam examples. And this is the only way for you to learn. Just watching someone else doing them will never help you to master them and to learn the essential skills. We'll be looking at the 3 most recent November exam questions. Question 5, averaging around 14 marks each. You can see from these snapshots, all 3 of them dealt with an object on an inclined plane. So as usual, please pause or stop the video here. You need 27 minutes to answer all 3 of the questions on pages 53 and 54 in your booklets. I'll not be dealing with the recall questions, and please also leave out the very last question, 5.4 on page 54, as there were some problems with it. So please do these yourself now before proceeding. So let's start with November 2018. Typical question with an object going up an inclined plane. You're told the inclined plane is rough, so that will tell you that there's frictional forces. And we're told that there's a force of 4.8 times 10 to the 6 joules, which moves, the amount of work done, 4.8 times 10 to the 6 joules, which moves the object from A to B. Now that work has to be done against friction. It also has to be done against the force of gravity. These are the equations we're going to be using. For 5.3, the average power, we'll just use power equals work over time. For 5.5, work energy principles, we're going to use the work done by a non-conservative force. So let's start with the simple ones. 5.2, is force F a conservative force? No, because this is rough. Also, any applied force is not conservative, so you can safely say no. Calculate the average power generated by force F. Well, all you need is these numbers here, that the work done from A to B is 4.8 times 10 to 6 joules in 90 seconds. Power equals work over time, 4.8 times 10 to the 6 over 90, which is 53,333.33 watts. Probably best expressed as 53.33 kilowatts, but actually any of these answers is fine. Now the second part, please notice it says use energy principles to calculate the total work done. So they don't want you to use equations of motion. You're also told that the speed of the vehicle when it reaches point B is 25 meters per second. Now, before we solve the question and just try to get the right answer, let's try to understand what is happening here. So we were told the work done to move the vehicle from A to B was 4.8 times 10 to the 6 joules. 4.8 million joules of work was done. We're also told that the speed on reaching B is 25 meters per second. So this work has had to do three things really. It's had to overcome friction, it's had to overcome gravity and lift the car vertically, and it's had to accelerate the car from 0 to 25 meters per second. At the beginning, we know that the potential energy was 0 because the initial height was 0. We also know the kinetic energy was 0 because the initial velocity was 0. At point B, we know the potential energy. We can calculate it quite easily because the height is 200 meters, and we can calculate that that was 2.94 million joules. We can also calculate the kinetic energy because we know the final velocity, and that was 468,750 joules. So the mechanical energy at the start was 0. Mechanical energy at the end was 3.408750 million joules. And that was the amount of work that was done by the applied force. So let's add up. The work done by the force was 4.8 million joules, but the total mechanical energy at B is only 3.4 million joules. And if we subtract, we can see that about 1.39 million joules is missing. And of course, it's not missing, it's been converted to heat energy, and that is the work done by friction in slowing down the vehicle. So the bottom line is, if we'd had the same setup here with no friction, the speed at the top would have been higher than 25 meters per second. So what the friction has done is effectively slowed down the vehicle. So I want you to understand where this figure comes from. Now, let's look at it again. And remember when we looked at the energy skate park, if you add some friction, as you can do, and I hope you'll take time to play with the simulation, what we find is that eventually the kinetic and potential energy get converted to thermal energy. And that is not useful. It's a dissipative force, the force of friction, and the energy is dissipated. In our exam example, it wasn't dissipated completely, but the final velocity was less than it could have been. So let's do it formally. Again, we've made note of all these numbers here. So we're going to use the equation that says work done by a non-conservative force is equal to the change in kinetic energy plus the change in potential energy. So the mass is given, final velocity is given, initial velocity is 0. That's one of the obvious features. Again, acceleration of gravity is given, final height is given, it's 200, initial height is 0. So like I said, it's a case of just keeping track of the different numbers. So let's fill in the numbers. So the work done by the non-conservative forces, there were two: work done against friction plus the applied force, both non-conservative forces. The total work done by them is half times 1500 the mass, 25 the final velocity squared, and that calculation there for potential energy. And putting all that together, we get that the work done by the frictional forces on the vehicle is 1.39 times 10 to the 6 joules. Okay, so it's taken away some of the energy which could have been available for accelerating this car to a greater final velocity. How are the marks allocated? It's worth 5 marks. First mark for just getting the extended form of the equation correct. Then 1 mark for the left-hand side, 1 mark for the first kinetic energy calculation, 1 mark for the potential energy calculation, and 1 mark for the final answer. Please remember, work is a scalar, and so we're not required to give a direction because there is no direction. Let's take a look at the November 2019 paper, question 5. So here we have a typical work, energy, and power question, just 13 marks. Again, it's an object on an inclined plane. You're told the object has a mass of 1.8 kilograms, slides down a rough curved track. Again, notice the word rough, meaning that there's friction, a non-conservative force, and it passes point A, 1.5 meters above the ground at a certain speed, and reaches point B on the ground at a certain speed as well. Now, they're going to ask questions about conservative forces and conservation of energy. And just remember, these are the equations that we're going to look at. On page 38, this is my condensed version of those equations. I want to remind you of a slide we looked at earlier in this video, comparing conservative and non-conservative forces. They almost always ask about these, so make sure you understand them. Remember, conservative forces, the example you'll come up with most often is gravity. And in that case, the work done on an object doesn't depend on the path taken. If you lift something up, it doesn't matter if you lift it straight up or take it up a ramp, but the path is not important and the energy is recoverable. Non-conservative forces, the most common example you'll find is friction. The path does matter and the energy is not recoverable because it's changed into unusable forms. That's why we call these forces dissipative forces. They dissipate or permanently take away energy from the object. And with conservative forces, mechanical energy is conserved. With non-conservative forces, it is not. That brings us to the first two questions, ignoring 5.1, the recall question. You can get that from the memo. Name the conservative force acting on the object. Well, that would be gravity, and that's the one that will come up time and again. 5.3 is mechanical energy conserved as the object slides from A to B. Well, it's a rough track. There's friction. So, of course, the answer is no. You do need to give a reason. So you need to say there's friction or say that there's a non-conservative force, either one of those. Then very easy, 5.4, calculate the gravitational potential energy of the object. All you need are these figures here, the mass, the height, and of course you need the acceleration of gravity. From your data sheet, U or EP for gravitational potential energy equals mgh. Mass is 1.8, height is 1.5, G is 9.8. Do the calculation and you'll get 24.46 joules. Very easy. And you're going to see that we're going to use that figure again. 5.5, using energy principles, calculate the work done by friction on the object as it slides from A to B. So once again, if there was no friction, we understand that it would have got to be with a higher velocity. So it has been slowed down by friction. And we want to know how much work was done by friction. Notice it's the work, not the force, which they're asking for this time. So there are the figures, and there are the figures that we need. And we can do some calculations. Your potential energy at point A is 24.46 joules. We already calculated that in 5.4. And of course, your potential energy at B is 0 because it's right at the bottom of the track. The height is equal to 0. So work done by friction is the work done by a non-conservative force, which is delta K plus delta U, change in kinetic energy plus change in potential energy. So do those calculations. In fact, it's easier to take M and mg out of the brackets. Final minus initial velocities squared, final height minus initial height. Now, I've put the final height in blue because we notice that that's going to be 0, and that term will actually disappear. Substituting in, mass is 1.8. You can see that a well-labeled diagram will actually help you to get the right numbers. Final velocity is 4, initial velocity 0.95. And then, of course, that figure of 26.46 is simply what we calculated in 5.4. We get minus 12.87 joules. Why is it negative? Because the object is moving to the left, whereas the frictional force acts to the right in the opposite direction. So if you didn't get it here, naught is just the potential energy at B, and potential energy at A, 26.46. We actually didn't do the calculation here because we'd already done it in question 5.4. And then just finally, Surface BC is frictionless. What is the value of the net work done on the object as it slides from B to C? For work to be done, you need a force and you need movement in the direction of the force. Well, there certainly is movement, but there is no force, because if it's frictionless, the object will glide, will keep the 4 meters per second, go at constant velocity with no net force acting on it, so there's no net work done. And to finish this video, a question from our most recent exam paper, November 2020, question 5. Once again, we have an object. It's a roller coaster car on a slope. Mass is 200 kilograms, and we can add that to our diagram here. Notice that the engine is switched off, so it's just in free fall, traveling along track ABC, which has a rough surface. Again, notice there's friction, non-conservative forces. At point A, 10 meters above the ground, the speed of the car is 4 meters per second. At point B, an unknown height h above the ground, speed of the car is 2 meters per second. Now they tell you that during the motion from A to B, 3.4 times 10 to the 3 joules of energy is used to overcome friction. So in a sense, that energy is lost from the motion of the car. So again, if there hadn't been friction, we would have expected the speed at B to be a lot higher than 2 meters per second. You're asked to calculate the change in kinetic energy of the car after it has traveled from point A to point B. That's a very simple calculation. You don't need any heights. We know the mass of the car. You know that the initial velocity was 4, final velocity was 2. We just take our formula for kinetic energy, half mv squared, and the change in kinetic energy is half m times v final squared minus v initial squared. Putting in our values, and just be careful to remember that the final velocity is this one, 2. Initial velocity is 4. So we're actually going to get a negative answer, and we get delta K is minus 1,200 joules. So its kinetic energy has decreased by this amount in traveling from point A to point B. Then you're asked to use energy principles to calculate the height h. Now again, please notice that. Don't use equations of motion. So we already have some facts that we know, and h is the unknown. We know that the initial height was 10 meters. This is the final height, and we don't know what that particular height is. So the work done by a non-conservative force from our equation sheet is delta K plus delta U. In this case, this is the work done against friction from A to B, and we were given that figure. So it's a change in kinetic energy, which we calculated in 5.2, plus the change in potential energy. Filling in the numbers, minus 3.4 times 10 to the 3 joules that we get there. Because it was done to overcome friction, it's a negative amount of work. Change in kinetic energy we calculated in 5.2 was minus 1,200 joules. The mass times gravity. Final height is unknown. That's what's required. The initial height is what was given. Do the calculation carefully, and you'll come up with the final height equal to 8.88 meters. That seems reasonable when you have 10 meters on one side and 22 meters on the other side. Note that it's only 4 marks, so it's likely that you'll use a calculation like delta K from a previous part of the question. Now, 5.4 was actually not marked. There was a problem with the question, and so it was left out and it was not marked. Please be assured that if the examiner does something wrong, that you will not be penalized, so don't worry about that. Always do your best and try a question, and don't worry if there's a problem with the question, you will not be penalized. So that's all for this video on solving equations, particularly for question 5 on work, energy, and power. I hope this has been helpful, but at the end of the day, the only way to make sure you have the essential skills is to practice, practice, and practice again.